In our final presentation for section 6.4, we'll discuss an application. We want to look at what is called simple harmonic motion and frequency, and we have a definition to begin our lecture. If an object is oscillating and its displacement from some midpoint at time t can be described by either f of t is equal to a sine omega t, or g of t is equal to a cosine omega t, the object is said to be in simple harmonic motion. In either case, a is a real number and omega is a positive real number. The amplitude of the object, the maximum displacement from rest, is the absolute value of a, and the frequency of the object's motion is omega divided by 2 pi. Now, this example is one that is difficult to look at in terms of the definition that they've given us. It's difficult to understand. So we're going to take our example and then flip back and forth between the example and this definition and try to explain what is going on. So our example is an example where we are going to put some potatoes into a basket on the grocer scale. And when we do that, the basket is going to bounce up and down. All right, so our problem says a first approximation to the motion of an object suspended at the end of a spring and set into vertical oscillation is given by, and so we have to start with kind of a format for a formula where y is the displacement of the object above or below its rest position, and a and omega are as defined on the previous page. All right, so we know that the frequency is 3 hertz, which means that the basket makes 3 up and down complete cycles each second. I'm just going to jot that down. Okay, and let's continue with our problem. On the next slide, it says, given that the distance traveled between peaks of the basket's oscillation is 8 centimeters. Okay, so what that means is that, and you can see that in the picture here, that when the basket is at its lowest point, it is here. And when it bounces up a distance of 8 centimeters. And so it's going to go back and forth between this low point and this high point. It's going to do that 3 complete times per second because that's the frequency that we're given. And we want to find a mathematical model for the basket's motion. All right, so we know that somewhere in the middle we have kind of a resting point for this basket, that sometimes when the weight is heavy it goes below and sometimes it goes above, but the resting position lies right in the middle of the 8 centimeters. So this says, from the given information we know that our model must describe an object traveling 4 centimeters above and 4 centimeters below its rest position. In other words, the amplitude must be 4. We have a choice to make, however. We can define our coordinate system so that a positive displacement is either up or down. Now, we're going to come back to that in just a minute when we look at the graph and try to explain what that's saying. All right, but right now, what we do know is that the amplitude must be equal to 4. Okay? So if I look at my model for my equation, I know that the A value is the amplitude. And so I'm going to be putting a 4 in front of that cosine function. All right, so I'm going to go ahead and kind of get this started. I'm going to write down the format that they ask us to use. And we know that the A value is going to be 4, so we can go ahead and plug that in. All right, so let's look at what the omega is going to equal. It says a frequency of 3 Hertz means that the basket makes 3 complete up and down cycles every second. So we've already talked about that. And then they go on to say, well, this means that omega is equal to 6 pi. All right, so let's look at how they're getting that. So if we go back to our definition, it says that the frequency of the object's motion is omega divided by 2 pi. Let me write that down. So we know that the frequency is equal to omega divided by 2 pi. So we know that the frequency is 3. So I'm going to go ahead and plug a 3 in for the frequency. And I'm solving this expression for omega, which means I'm going to multiply both sides by 2 pi. And so 2 times 3 is 6 pi, and it's going to cancel over here, and we have our omega value. All right, so that's where this comes from. And now we're just going to plug that in. So we have our model looking like y is equal to 4 cosine. In place of the omega, I'm going to put 6 pi, and I'm going to leave the t because the t is our variable. Okay, so now that we have our model, which is what they were asking us to find, let's go ahead and take a quick look at the graph for this function. All right, so I'm going to turn my calculator on. I am going to put the function in 4 cosine 6 pi x. We can't really use a t on our calculator, so x will play the role of the t. And let's take a look at the graph. Okay, so what we have is on the x-axis, this is our resting position for that basket. We know that at its highest point it goes up 4. So we've got 1, 2, 3, 4. And at its lowest point it drops down 4. So 1, 2, 3, 4. So that makes sense. I have my window set on the x to go from 0 to 1, right? Because we were talking about 1 second. And so we can tell that this graph is going to make 3 complete cycles. We've got 3 complete cycles being done in that 1 second time period. Now, if you remember, they told us that we had a decision to make about the amplitude. It said we had a choice to make. We can define our coordinate system so that a positive displacement is either up or down. So essentially what this is saying is that it is possible to either start the scale in an up position or start the scale in a down position. And it's really equally okay to do it either way. So if I had started it in a down position, that would have meant that instead of a positive 4 as the amplitude, that we had a negative 4. And so all that's going to do is start the graph at a bottom point instead of at a top point. Okay, it still gives us 3 complete cycles in that 1 second time frame. It still gives us a high point of 4 and a low point of negative 4. And so they're basically telling us that either option is considered acceptable for a problem like this. Okay, so the last thing that we want to look at, and we're just going to talk through this really quickly, is the idea that as this basket bounces up and down, eventually it's not going to bounce up to 4 and bounce down to -4, but that it's going to start to kind of level itself out, and eventually it will stop bouncing altogether. So on this, we are asked to graph the function -4 e to the negative t cosine 6 pi t. Now, the only difference between this function and the one we just graphed is that e to the negative t. Okay, so you can see that what they've basically done is they've just added in, or actually multiplied in, e to the negative t, but the rest of our function and their function is exactly the same. And so the reason that they did that is because that factor of e to the negative t provides that damping effect. Okay, so it says that right here, that the reason that they did it is because that is going to damp out the graph, which means that that slows down that oscillation. And so if we graph that, we can see that coming into play. Here's our original graph stretching up to 4 and to -4. And you can see as the time gets longer, the oscillations get smaller and the amplitude decreases. And that is the effect of the e to the negative t in that function.